recording so we don't screw up. Okay, last time we talked about the horizontal axis of the spectrum. We solved the Schrodinger equation. We had to build a wave function to do that, so we built the wave function for the particle in a box. And we were kind of rushed at the end. The differences in those energy levels is the spectral line. And it kind of showed the transition equation for that. We'll be doing that multiple times throughout the semester. On the homework, it's using the rotational energy equation. So you'll have to compare the homework problem to the one that's in the lecture. The lecture uses the particle in a box energy equation. The homework uses the rotational energy equation. Okay, and so how do you do that? Well, if you're talking about the difference between E1 and E2, let's do E2 minus E1. Okay, so this is delta E. And we know that the energy equation is equal to some constant out front times J plus 1. Right, so that's the energy equation for rotation. We have a rotational constant, and then the rotational quantum number is J. Okay. And we know if we're going to be, let's do it in a general case. Let's do it as E of J plus 1 minus E of J. So what does that mean? That means we're going to have the energy equation written with J, and then the energy equation written with J plus 1 everywhere there's a J. So let me just set the problem up, and then you can do the algebra on your own. So this is equal to B. So see, everywhere there's a J, we're going to put an extra plus 1 in there. So it's B times J plus 1 times J plus 1 plus 1. Where did that come from? You see there's a J right there and a J right there, and both of those get that extra 1 in there. So we're saying it's whatever J level I'm at plus 1. That's the upper state. And we're going to subtract, let me close the parenthesis, we're going to subtract the energy equation. So we're going to have B times J plus 1. So that's the algebraic setup for all of the delta J equals 1 transitions. We're going from J to J plus 1. What's the difference? We've set it up algebraically. Now it's just a very simple math problem, right? Go ahead and multiply your J plus 1s times J plus 2, and then subtract all the like terms, and then you simplify, and that's what you're doing. So that is the general transition equation, because it's all the possible transitions that hop one level. You can have all the possible transitions that hop 2 levels by putting in J plus 2s everywhere, or 3 levels by putting in J plus 3s. So these are called transition equations. They're the equations for those differences in the energy levels, and that will give you the locations of your peaks on the horizontal axis for this whole series. So that's the horizontal axis, the transition equation. Now let's look at the transition dipole moment integral, which tells us the intensity on the y-axis. So that's what today's lecture is. We did the horizontal axis last time. We're going to do the vertical axis today. But first, there's going to be an announcement. Next Monday and Wednesday are video only. So those lectures have been recorded. They're on Blackboard. I'm going to be at a conference. I'm the chair of the Parts Cleaning Conference. And we have our largest show ever in the whole world, the International Machine Technology Show. It's in Chicago. And so I'll be there running the sessions. I introduce the speakers. This whole year we've accepted abstracts and picked the talks and crafted the cleaning show. And so then we're gonna go and have a conference on industrial cleaning. So I got a picture of one of the prototypes of the James Webb Space Telescope. So that big mirror in the back is like a quarter scale model of it. So they had to test their procedures and their cleaning, all of that, all related to making those perfect mirrors for that telescope, which is doing such great work right now in space. Anyway, I saw that. I was like, I got to get a picture with that. And then this is pretty cool. This is the scale of what's going on at this show. That's a robot. You've seen robotic arms before, but have you seen one that's lifting 1,000 kilogram payload? Yeah, and making it look easy, right? And looking for scale, you can see the size of the people. You know, it's in a big box because that thing would kill you. You stepped in front of it. So anyway, it's going to be exciting. I'll take pictures and I'll show you some. Okay. So let's get back to the matter at hand. So again, we're dealing with spectroscopy. In order for a particle to interact with light, there needs to be three things really that happen. Okay, the particle needs to interact with something that light is. Okay, what is light? It's electromagnetic radiation. So what does that combination term mean, electromagnetic? Well, there's an oscillating electric field. So as light propagates through space, there's an electric vector, oscillating electric field. So it's like a positive charge or negative charge. It alternates, positive and negative. And how frequently does it alternate? That's the frequency of light. So if it goes through 50 cycles per second, then that's 50 hertz. Okay, so we're dealing with terahertz or even greater than that, exahertz in the visible spectrum. And so if you've got an oscillating electric field, what is the easiest way for something to interact with that? To be charged. If you have a charged particle and it's experiencing alternating plus and minus fields, that particle is going to start to oscillate too. So molecules, atoms, ions, they have electrons, they have protons, they have electrical particles in them, so they interact with light. Okay. If something doesn't interact with light, we call that dark matter, like a neutron. So a neutron floating around in space that's been blasted out of some star, that's dark matter. So you hear about that in physics all the time. It's just floating around and we can't tell it's there with light because it's dark. It doesn't interact with light. Okay, but we can tell it's there by gravity. So things will experience the gravitational mass of a neutron, but they won't be able to interact with it using electromagnetic radiation. Now there is also a magnetic field 90 degrees to it. So as the electric field is maximum, the magnetic field is zero. And so then as the electric field decreases to zero, the magnetic field is the maximum. Okay, and then so we might say this is positive, this is north, then this is negative, and then the magnetic field goes south. So you have magnetic poles north and south, and then you go positive, north, negative, south. And so light goes through space like this. I worked on that for many years. So then let's take the easiest situation, like our situation, an electron on a wire. That electron's charged. Okay, so we have to have an interaction with the electric field or magnetic field. The interaction with the electric field is about 1,000 times stronger than the magnetic field, so we don't do a lot of magnetic spectroscopy. NMR is one of those, but we're really not using the magnetic field to interact with the protons and the nuclei in NMR. We're just putting in a magnetic field to separate the nuclear spins and create an energy difference between them in a magnetic field. So it's still electromagnetic radiation or the electric field that we're interacting with in NMR. There's got to be an unequal population of energy levels. So when we did that, remember that diagram that we had where we had 8 different transitions, 7 or 8 different transitions, and the first 2 was absorption and stimulated emission. We talked about the laser, okay? They had the same probability of occurring. So if I've got a particle in the upper state and a photon comes in, that could drive that photon down to the ground state and I could amplify the light. Or if I had one in the ground state, it could absorb that light and the photon would disappear. If I've got equal populations in the excited and the ground state, equal, okay, then half the photons that interact may get absorbed, the other half may multiply, and I wouldn't be able to tell that light interacted with the substance at all. Because I would have some of those photons multiply the light and other photons take away the light, and the net sum would be 0. We call that spectral saturation. So if we get 50% of our molecules, atoms, ions in the excited state, then the signal goes away. We don't see net emission or net absorption because we've saturated the system. So we need an unsaturated system. We need to have, for absorption, we need to have more atoms, particles in the ground state or lower state for them to absorb. Then we'll see an absorption signal. It makes sense, right? We're trying to look at the lost light. So we need to have a situation where we will lose light. We need to have a situation where things can absorb. If we were looking at emission, like in a laser, we want more molecules, atoms, ions in the excited state so that we get an amplification of light and we see the lasing effect. And then we need a significant probability for the transition. So the transition has to be allowed. not every transition is allowed, and we'll learn that today. So we have these things called selection rules. How can the math will select which levels are allowed? So that's when we talk about selection rules, I like to think of it as the math is doing the selecting, okay, not us. Okay. So here's all the possible transitions in the particle in a box. So we've got just the first 4 wave functions, and we can have absorption and emission. And we have, this, let's just look at them. So we've got, 1, we could go from 1 to 2, 2 to 3, 3 to 4. So those are delta n of +1. What if we skip levels? Okay, we could go 1 to 3. We could go 2 to 4. Now we could keep doing that, but we only show 4 wave functions on the screen, so I'm just showing you the ones that are allowed for the screen. We could have 5 and 6 and 7, all those other wave functions. Okay, and then if we skip 2 levels, we could go 1 all the way up to 4. Okay, so these are all of the options that we have for 4 wave functions. Now we can write those down, but does the math allow them? That's the question. So we want to find the selection rules for this. Are all of these transitions possible? And those are just the absorption ones on the left. The emission ones are on the right. And so we can look at those as well. We have all of the things that we need. We've got charged particles. Check. We got an electron on a wire. Okay. We've got an unequal population. Boltzmann's distribution tells us that there's more in the ground state than the excited state, and it's a function of temperature. Okay. And then we have the probability. That's the question. So this is the math that we're doing with the particle in a box. Wave functions is that transition moment integral to see if the math will select all of these transitions or only some of these transitions. So this is the transition probability. It's we call that intensity. That's why I gave it an I. Remember we had the absorption. We want to go big, right? They have the Boltzmann piece, the I piece, the integral or intensity piece, and then the G is the line shape function, the Gaussian curve. So this number of molecules in the initial state is determined using the Boltzmann distribution. That's the unequal population piece. And then this probability piece is the square of the transition dipole moment integral. So you can think of I as either intensity or integral. It works both ways. Okay. And this is that integral. So it's sort of written out. You've got wave function, like the lower state wave function, the upper state wave function, and then this thing in the middle, it's just, that's not times, that's x. Okay. So just like this is a wave function that's plotted along the x-axis, this is the x-axis. We're just multiplying it by whatever x position there is. Okay. And that sounds strange, so let's figure out why we would do that. Why would we put x in the middle? This is the Boltzmann piece. It's the temperature dependence of the population of the energy levels. Okay. So let's expand upon this integral piece. So why do we use x to represent light? So light's coming into our system. There's a couple of different easy ways to think about this. How would we get the maximum value for light interacting with our wave function? Okay. So the way to perturb that wave function the most is for one side of the wave function to be charged positive and the other side of the wave function to be charged negative. So you can multiply that wave function by the x-axis because the x-axis has a positive end and a negative end. So that's the mental thing. I don't want you to think of that x in the middle as the x-axis. I want you to think of it as positive and negative charge. Okay. And since we're doing proportionalities, I have an equal sign up there, but it really should be proportional to this integral squared, then it doesn't need to be an exact number. It just needs to be proportional to all the other possibilities. And so we can just say that we'll use this x-axis to represent our electric field. Because an electric field has a positive and negative end, 2 poles, right? And so does the x-axis. It has positive numbers and negative numbers. And that'll do it. It's a dipole assumption, as we call it, or a dipole approximation. So we're going to approximate that electric field of light with the x-axis. So light is an oscillating electric field. we're going to ignore the magnetic field. And so if we take a snapshot of light at its maximum value of its electric field and put that along the x-axis, then that will be the best result for calculating the intensity or probability of a transition between two energy levels. So we have two energy levels, the n and n prime, and we're just doing that. If we multiply those three functions together and integrate over all space, if that result cancels out and it ends up being 0, there's no probability that light can get that molecule, ion, electron from state n to n prime. If it's non-zero but small, then there's a small intensity for that peak. If it's non-zero and huge, then there's a huge intensity for that peak. So this allows us to get the different intensities for all of our transitions. So this is the integral. It looks bad in a sense because it's on the screen and there's lots of letters, but it's not bad. This is so simple. It's one dimension. Remember, if we were trying to do this in 3 dimensions, we'd have a triple integral. And we'd have all of these angles, longitude, latitude, and radius, and all of this business. Okay, so this is a much easier integral. We can actually do this one. The ones in 3 dimensions they're very difficult, and you have to make a lot of approximations and just cut back the math. Okay. Notice I've done this for the general case. So I've done this for not just n and n prime. I went ahead, instead of n prime, I used this n plus delta n. Okay. So delta n could be, a change in like between adjacent levels. So delta n equals 1 would be all the transitions from 1 to 2 or 2 to 3 or 3 to 4. So if delta n equals 1, then we'd have those transitions. If delta n is 2, then it'd be going from 1 to 3 or 2 to 4. Okay. If delta n is 3, it'd be the 1 going all the way to the 4. So we're going to solve this integral in a general case with delta n's to kind of see how this figures out for all of those possible transitions. Now this is in the book, so after 4 pages of calculus and algebra, which again is only 4 pages, if you were doing the 3-dimensional case, I don't know how long it would be, okay? But in the book, in the chapter that you have, I don't skip any steps, and I even color-coded some of the integration by parts and things like that, so you can see the math. And you will do it yourself by hand in 3 weeks in the lab, so you would kind of get a feel for it. So after that, this is the result that we end up with. So after all of the integration and the trig substitutions and everything like that, we end up with this result. And instead of signs, remember in the particle in a box, the normalization situation, or maybe it was the Schrodinger, let's see, what was it? Was it showing it was orthogonal and normalized? We had sine of integer multiples of pi, and those were all 0. Well, now we have cosines of integer multiples of pi. And they're not all 0, but they are nice and easy. They're either +1 or -1. So if we look at cosine, you see whenever it's an even multiple of pi, then it's +1. Whenever it's a negative or an odd multiple of pi, it's -1. Well, if it ends up being +1s, when delta n is even, so for changes of delta n equals 0 or 2 or 4, then this piece right here gives us a +1, and then this is a minus sign, and that's a +1, so this term goes to 0. And then the same over here, whenever it's even, this term is +1, and so 1 minus 1 is 0, so the whole thing evaporates. It turns to 0 whenever we have a delta n of an even number. So if we're trying to go from 1 to 3, that's a delta n of 2. The math says that's not allowed. The intensity is 0. So even if the photon of light matches that difference, the wave functions won't let it jump. So we're doing the math of that quantum jumping that Schrodinger was so irritated about. We still don't know why it jumps. Light comes in, this particle sees light, and there's a probability that it will jump, but we don't know about individual particles whether they will jump or not. But this is the result. When delta n is even, all of those terms go to 0. When delta n is odd, then we end up with like a minus 2 and plus 2, and then you do the algebra, and this is what you get. Okay, so this is the intensity of those transitions. And it's a function of L, so the box length is in there. It's a function of what quantum state you're starting at, and also how many levels you're trying to jump. But we know all these terms. We know L, we know what pi is, we know N, and we know delta N, how many levels we're trying to jump. So we can put those numbers in there. And this is just telling us, though, the end result, the selection rules, the mathematical selection rules are that this transition is allowed when delta N is odd. So plus or minus 1, plus or minus 3, plus or minus 5, and so on. So we can go up or down. Notice that the N's are all squared. So there's no difference in a absorption or emission. So delta N could be minus 2. It could be going from 3 down to 1. But since it all depends upon delta N squared in some manner, then there's no difference between absorption and stimulated emission. So that tells us these probabilities are the same up and down. For odd transitions, we see that they're allowed, meaning they're non-zero. So if we pick a 7 angstrom box and we're dealing with an electron, then these are the results of those integrals. So I went ahead and put in the numbers. And so this is the intensity for the 2 to 1 transition. So 1298. It gets a little bigger for the 2 to 3. For the 1 to 2 transition, it's 1298. For 2 to 3, it's 1514. For 3 to 4, it's 1576. But they're all pretty strong. And so delta N equals 1 are the strongest transitions. And then look at the delta N equals 2s. Those are forbidden by math. Okay. And then delta N equals 3 is 8.3. So yes, we can skip levels, but look at what happens to the intensity. It goes from 1500 down to 8. So it's a very weak peak. So if we're looking at a spectrum, all of the major peaks are going to be adjacent quantum states. There might be a tiny little peak, and we say, well, what is that? I can't fit it into my model. Well, don't forget, you can jump levels. And if you're jumping a level, maybe that's that tiny little peak. It's what we call an overtone. It's jumping multiple quantum states. So this is explaining a lot of the features we see in our spectrum. You're just using the particle in a box. So we have this probability equals 0. So that's an interesting fact that the math can eliminate some of our potential transitions. This is great because it greatly simplifies the spectrum. Notice instead of having instead of having 6 peaks, we only have 4 because of the math selection rules. And one of those is really weak, so we really only have 3. Yes.
Is there like a reason besides math that it's easier to go like 3 energy levels instead of 2?
No, it's just the math of those wave functions that's not allowing it to jump 2. Yeah. So if you think about the waves and how waves interact with each other, sometimes they cancel each other out, and that's what's happening. So it's the wave functions that just aren't lining up for a double jump, like going up 2, but they do line up going up 3, but they don't line up very well, and so that's why the intensity is small. So this lining up that I'm saying, it's called the overlap. So whenever you're multiplying waves times each other, the positive parts, when they overlap, get more positive, and the negative parts, when they overlap, get more negative. But if it's the reverse case, the positives multiplied by a negative part can cancel, and that's what's causing it to drop out. So after we did all that calculus, we end up with the cosines and the plus and minus ones. That's showing you that there's certain times when they cancel perfectly, and those are the delta N equals 2s, that they're just canceling each other out. So that was the beauty of thinking of nature as waves, because we could explain this bizarre thing. Because why wouldn't nature allow something to go from 1 to 3? I mean, what does nature care, right? Well, if it's a wave function, then the waves may not allow it, and they don't. So it's like the the math or the wave functions are selecting which transitions are allowed. That's why I want to try to keep using that word selecting, because they're called the selection rules. I just want to hammer that into your head. The selection rules are the ones that are allowed. And it's the wave functions and the math that's doing that. And then we'll look at symmetry, and symmetry can explain all of this very simply. Yes?
Is that only true for the one-dimensional one?
No, and that's the beauty of this. So I'm showing you the one-dimensional case where it's perfect, okay? And in symmetric molecules, big, huge molecules, it can still be perfect, like for benzene, you know, very, very symmetric molecule. And you'll have more than half of the levels just not even be allowed for the transitions. So the vibrational spectrum for benzene is very, very simple. It only has like 3 peaks or 4 peaks in the infrared. If you take a hydrogen off and put a chlorine on, you've broken the symmetry. And now you've got like 20 peaks in the infrared. So, and that's one of the labs that you'll do. You'll look at the difference between chlorobenzene and benzene in the spectrum, and you'll see all of these different peaks in the chlorobenzene spectrum, and the benzene spectrum will be really simple with like 5 peaks. So we'll actually get to see it in a big molecule, not just the particle in a box. But there's no way, well, no way for me to do the math on benzene, and I would question anybody that says they could do it, you know, from first principles. You know, we do it all numerically in Gaussian, so that there is a way to do it, but we do it numerically. Okay, this is also interesting that because it's delta n squared, it doesn't matter if it's going up or down. So delta n could be negative, and you get the same intensity. So absorption and emission probabilities are equal to each other. And it's also interesting that the skipping of levels is much less probable, so that's why the intensity is really small. And the waves just don't overlap as well. So I know you know, quantum mechanics sounds really daunting, but this is it, guys. You've done it. So just thinking about nature in terms of waves explains these spectroscopic phenomena. And this is it. This is as complicated as it gets. A couple of integrals. Schrodinger equation, intensity equation, that's spectroscopy. That's it. That's why I wanted to show it in one dimension. Because you can get your mind around a guitar string, right? You can see it, you can video it, you know, you can think about that wave. And if we think of nature that same way, the analogies that we can make, if we understand the one-dimensional particle in a box, we can understand what benzene's doing, even though benzene's crazy complicated, okay? Let's take all the hydrogens out and put chlorines around it. So now it's the same symmetry, but I've got heavier masses. What happens to the vibrational frequencies in the spectrum? Well, let's think of the particle in a box. Mass is in the denominator of the energy equation. So if I increase that mass, what happens to the energies? They decrease. And those vibrational frequencies for carbon chlorine stretches are really low frequency. For hydrogen, 3,000 wave numbers. For chlorine, 700. Or something even below that, maybe 200. I don't remember it, but it's really low. And how would you guess that? Well, mass is in the denominator in the particle in a box. Well, it's also in the denominator for vibrations. In fact, mass is in the denominator for all the energy equations. So if you understand the particle in a box, you can make analogies to the most complicated systems. DNA, it doesn't matter. So this isn't just like a curious, simple problem that we did just to show that we can do one of the problems. Learn this by analogy, and you can apply the thinking, the energy equation for the particle in the box, you can apply that as your chemical intuition. So I want you to graduate with your bachelor's with an intuition as to how systems will operate, okay? If you want to go on to graduate school, maybe then you get a little deeper into the math and you do the full triple integrals for the hydrogen atom and everything, and you'll get a deeper appreciation for three-dimensional wave functions. Okay, that's great. But at the bachelor's level, I want you to come out with an intuition. It's like, you know, I don't know how to do that particular system, but I know that mass is in the denominator of all the energy equations. So if we take a hydrogen off and substitute a deuterium, I bet the frequency of whatever we're measuring is going to drop. And it will. Okay, so this is a bit of review. So what determines the peak location? That's that transition equation. So the difference in energy levels tells us where those peaks will show up on the horizontal axis. Okay. So we took the delta E, converted it to wavelength, And so this would be the wavelength for the 1 to 2 transition, the wavelength for the 2 to 3 transition. This integral overlap, remember we did the first 3 transitions for the particle in the box and they kind of went up. It was 1298 and then like 14 and 1500. So it kind of went up, and we do see that right here. We see this is like 12, what was it, 1298? And this was like 1500. But why is this one lower? Well, because of the Boltzmann distribution. Okay, this one is starting in level 3 and going to 4. And at whatever temperature we're at, 500,000 Kelvin, there's just not as many electrons in level 3 as there are in level 2 or level 1. And so for the absorption profile to be the sum of the multiplication of B times I times G, that Boltzmann term's been multiplied by all of those I's. And so that's why they drop off. The I intensities increase as you get smaller. So I kind of goes up like this. But the Boltzmann piece drops it down to 0 and forces it to 0. Because at a given temperature, you're just not going to have electrons excited way up there. If we cool this down to room temperature, we only have 1 peak. Because at room temperature, there's not even any electrons in level 2. So the Boltzmann factor would look like this at room temperature. It would just go like this. It would go. So as we increase the temperature, it allows more transitions to take place. So this is higher and higher temperature. It's getting busy here. Increasing temperature. I don't know if you can read that. I can't even read that. That's what I tried to write, increasing temperature. So the Boltzmann factor thing is going like this, allowing more transitions to take place as you increase the temperature. Why? That's the population piece. More electrons are finding their way to the excited states at higher temperatures. If you cool it down, they're not up there, and so they're only in the ground state, so you only have the fundamental, the very first transition. You cool it down to absolute 0, they're still only in the ground state. And so this peak just sits there. Even at absolute 0, you will still have 1 peak. You'll have the fundamental transition. So the transition equations is what I was just talking about for the x-axis, or I keep saying x, but I mean to say horizontal axis. I don't want to confuse the x of the particle in a box with the x-axis of the spectrum. So I'm trying to be precise. The horizontal axis of the spectrum is the transition equation. You could do it in terms of energy, you could do it in terms of frequency, you can calculate it in terms of wavelength. Okay? And these are the general equations with using delta n's. Okay? And so here is just what we call a stick spectrum. So that we've gotten rid of the G. So we have the I and then the B, the Boltzmann term times I. And then you just have sticks for all those transitions. I did this just to kind of simplify things. The blue ones are the delta n equals 1. Then the green ones are delta n equals 3. And the red ones are delta n equals 5. And so you can really see the relative intensities of those. So these are all allowed transitions. Notice we don't have any 2s, 4s, 6s. We're not changing by 2, 4, or 6. The intensity of those would be 0. But you see that the blue ones are all of those delta n equals 1. They're the strongest peaks in the spectrum. Then the overtones are really tiny. So we see those. The only spectroscopy that I think we come across where we see overtones is in infrared. So we'll see overtones in the infrared spectrum. This is so if we put in the delta n equals 1, like we could calculate those transitions based upon the length of the box, the mass of the particle, the delta n, and the initial state that we start in. So we have the general transition equations for all of those peaks. Here's the delta n equals 3, and then here's the, well, I guess I didn't write the 5 one. So sort of showed this spectrum, and now I've shown it with the quantum numbers labeled on there. So whenever we do a spectroscopic measurement in the lab, a lot of times we will do what's called peak picking. We will assign the spectrum. So this is what you would do to assign the spectrum. You would assign quantum numbers to those transitions. Do you see the pattern? The very first one is the 1 to 2. That's called the fundamental transition. The ground state to the first excited state is the fundamental transition. We saw that on the previous slide. Let me go back. Whoa, it's trippy. Okay, you see that first peak is the fundamental. All of these peaks only exist if it's hot enough. So those are called hot bands. So this is big time vocabulary here. Okay. And then here's the overtones. Okay. This is the first overtone and the hot bands of the first overtone. So again, those other green ones would only exist if it was hot. You can always have the 1 to 3, let's see, 1 to 4 as your first hot band because it's starting in 1. So you can always have an overtone, at least one overtone. But if you wanted to go from 2 to 5, it needs to be hot enough to get a molecule or an atom up into the level 2. So these are the hot bands of the first overtone. Then in the second overtone, this first red dot is going to be the second overtone, and then you have the hot bands of the second overtone. So anything starting in level 2, 3, 4, or higher, those are all hot bands. Okay, and whether it's this fundamental or just a hot band itself would depend upon the quantum states that it's starting in. So here's the assignment of that spectrum, and you can see why those are hot bands. See, this one starts in level 2, this one starts in level 3, starts in level 4. So if we cool it down, those will disappear. I also put, made it as complicated as possible, not just to make it complicated, but to show you where the wave functions are, right? The wave functions are on the horizontal axis of the spectrum based upon the energy. So this is the energy, the Hamiltonian. This is the Schrodinger equation for state n prime, and this is the Schrodinger equation, expectation value, Hamiltonian times the wave function, left multiplied by the wave function and integrated over all space. So you have wave functions all over the x-axis, horizontal axis. And then on the vertical axis, you have the wave functions. Here you have the lower state wave function and the upper state wave function all in the same integral. And then x is representing light. And then you have the energy of the lower state in the Boltzmann distribution, which is also using the wave function. So you see, you can't explain anything about spectroscopy without an understanding of the wave nature, the wave properties of nature. So then after multiplying by the Gaussian, this is that same previous plot. So see these blue lines, green lines, red lines? Those are these vertical lines right here. And you just can't even see them. There's a bunch of little pluses down here, but you can't see them from where you're at. We add in the Gaussian, sum over everything, we get the absorption spectrum. And it looks very similar to that black body radiation curve. So that's what's going on with spectroscopy. Now, sometimes we don't plot by wavelength, okay? If we, like in infrared, we plot versus wave number, okay? And that's proportional to energy, because it's wave number is 1 over the wavelength. So we would see equally spaced transitions. So this is the same spectrum, just plotted with a different horizontal axis. This is plotted with transition energy on the horizontal axis, as opposed to transition wavelength. Okay. So where's our fundamental on this one? Our fundamental is that very first peak, the lowest energy difference, and then they get higher as you go, and you see they're equally spaced. Okay, so those are the hot bands. These are the overtones. So this is the first overtone, and this from here going up, these are the hot bands of the first overtone. The first one is not a hot band, but the second, third, fourth, or whatever are the hot bands of the first overtone. And then here's the second overtones, these red ones. Do I have that one? No, I don't think so. Yeah. Well, here I can show it on this. This is fully assigned. Every quantum difference is shown. So you see this overtone here is the 1 to 4 transition. It's not a hot band because it starts in the ground state. But this one is the 2 to 5. This one's the 3 to 6, the 4 to 7, 5 to 8. These have to be hot enough to get electrons up into those levels. So those would be hot bands and overtones. I'm emphasizing this because you'll have a homework assignment and an exam question where you are assigning these peaks with their quantum numbers and answering questions. Is it a hot band? Is it an overtone? Oh, it's both. You know, like this one, if I had multiple boxes to check, I would say, yes, it's a hot band and it's an overtone. This one right here, that one's just a hot band. This one right here is the only one I can label fundamental. It's just the ground state to the very first excited state. So 1 to 2. This one right here, 2 to 3, it's just a hot band. So this is what we do in spectroscopy. Now, why do we do this? This is the data that we have. We get a spectrum, we assign all the peaks with quantum numbers. It's not just like a Sudoku puzzle, okay? We go through and peak pick it and assign it, and then we can do like a linear regression of these peak positions. And if we do a linear regression based upon n in these peak positions, then the slope of that trend line has something about the molecule in it. In other words, it tells us something about the mass of the molecule and the size of the molecule, because L is in there too. So if we want to know about the mass of the molecule or the size of the molecule, we take a spectrum of it. If we can assign the quantum numbers to that spectrum, and we know something about the energies that we're dealing with, like the energy equation, we can pull out the physical properties. So this is the way that we use spectroscopy in science, is we'll measure the spectrum, assign the quantum numbers to those peaks, and then we'll pull out the physical information about the system. So that's the goal. So we can do that for the hot bands too. That's why I've shown the color-coded equations. Okay. But you see the mass is in every one of those, the length is every one of those. So we could learn about, and it's really crazy. You guys are going to measure the bond length of carbon monoxide. And I mean, you can't even see it, but you can measure its bond length to like 4 or 5 decimal places in angstroms. So an angstrom is take a meter, divide this in 10 to the 10th increments. That's an angstrom. So an angstrom is 1 times 10 to the minus 10 meters. So it's, the tick marks on there are, there's 10 to the 10 tick marks. That's an angstrom. And you can go like 3 orders of magnitude smaller than that, 4 if you're good. So with spectroscopy. So that's a really small ruler that you can measure. You can measure the bond length and know it really well. So from your laboratory, this is what you will do. You'll take the rho vibrational spectrum of carbon monoxide. You'll assign the frequencies. So you'll pull the frequencies out of this spectrum and make a table. And then you'll plot those frequencies versus the quantum number. And when you do a regression, doesn't that equation look like a nice linear equation? It looks a lot like y equals mx plus b. So you can do least squares on that, and you can get m and b. And both m and b contain information about the bond length and the mass of the particle. So that's what we're going to do. So we're not going to really, the particle in a box is the mathematical model we use to get our intuition. Okay. Now on Monday's lecture, it's a video lecture, but on Monday's lecture, we'll show how we can take 4 pages of calculus and reduce it to a Post-it note using symmetry. So that's pretty cool. So, download the notes and get it on your computer and do it just like you're sitting in here. Take your notes on the video, and then to cement that information, your lab next week will be on symmetry as well. So you'll learn how to do this with molecules, not just a particle in a box. Okay.
Can you
Yes.
clarify, where exactly the overtone is starting from the hot band?
Yes, so let me go right here to this one. This is fully assigned, okay? So this is an overtone because it's not just going by 1, it's going by 3. It's going from 1 to 4, so it's delta n equals 3.
Overtone is always delta n equals 3?
3 or 5 or 7, it's the multiple level jumps.
So,
See, these only change by 1. This is like 1 to 2, or 2 to 3, delta n equals 1.
okay.
So the overtones are when that delta n is not equal to 1.
The
When
very
it's-
first one that's not equal to 1?
Yeah, so the very first one that's not equal to 1 is your overtone. So 1 to 4 is your overtone. This is an overtone too, but it's also a hot band. It's both categories.
And why is that one the hot band as well?
Because it starts in level 2.
So, hot bands are anything besides n equals 1?
Yeah, so the starting level, if it's the ground state in our system, is ground state is n equals 1. Anything above that is going to have some temperature associated with it, or that molecule or electron won't be in that level. So it's a hot band, right? You wouldn't have an electron in level 2 if it wasn't hot. So we cool everything down, everything drops into the ground state. And we only have those blue peaks. And we only have this one, none of those, this one, and none of those. Because those are all hot bands of the overtones. So we would have one big peak here if it was really cold, and a tiny peak here, and a tiny peak here. Because those all start at n equals 1. So there's no hot bands of anything, no hot bands in the first series, and no hot bands in the overtones. Yeah, because it's not hot. But if you heat it up, then you start getting the hot bands. Yes.
So how come on this one, whenever we started with the overtones, we went left to right, and then the wavelength one, you said the first overtone was like the farthest out?
Yeah, because energy and wavelength are inversely proportional. So the whole x-axis flips when I turn it to wavelength. Yeah, and so it matters. That's why I do that, because if you're in UV vis, the horizontal axis is wavelength. So your fundamental will be at the longest wavelength. And if you're in infrared and you're plotting wave number, which is proportional to energy, then your fundamental will be on the left. Okay, at the lowest energy. Yes. So lowest energy, longest wavelength. They go together. Yeah. Yes.
So it's like starting with the 1 to 6, is that the second overtone?
Yeah, it's kind of weird. It's the second overtone. Yeah.
So is that just because it's delta n is 5?
Yes. Yeah. So the very first time you can skip is a delta n of 3. So that's the first time. So that's the first overtone. And the delta n of 5 would be the second opportunity, or the second allowed delta and that would be the second overtone. Yeah. And then 7 would be the third. If it jumps 7 levels, then it would be the third overtone. Yes.
Are overtones always at such low intensity?
Yes. So we really don't. I mean, it sounds like I'm really emphasizing them, and I am for the homework. But in nature, we don't see them very much. So it's not like a huge feature that you're going to bump into all the time. You do see them in infrared, but they're small. But sometimes you're looking at an infrared peak, and you're like, is this an impurity? And you clean your solvent, and you look at it again, it's still there. You're like, oh, dang, that's an overtone. I've been distilling my solvent trying to get rid of this peak that I don't understand. Like, this is the CH stretch, that's a carbonyl. What's this little bump? And it happens to be an overtone. Yeah. Cool. All right, y'all had good questions. That was great. I'm thrilled.